This is the second video for section 3.4, annuities and sinking funds. In this video, we will cover the following objectives. We will calculate the future and present value both of an ordinary annuity and an annuity due. The careful reader and video watcher will notice that we haven't solved for the variables n, r, or m yet. This is on purpose, so solving for n requires the use of logarithms. Solving for r or m is beyond the scope of what we will do in this text. Example 3. Use the appropriate future value of an annuity formula and the given variables to solve for the missing value. Round to the nearest payment. So if we're told the future value, the regular payment, the compounds per year, and the interest rate. Payments are made at the beginning of the compounding period. So you'll notice the piece of information we're missing is n, which goes in the exponent. So I will start by selecting the appropriate formula, and here's the appropriate formula. Again, I choose the formula based on whether payments are made at the beginning or the end of the compounding period. At this point, I can substitute the values that I'm told. So that's the future value, the regular payment, the interest rate, which is 1.75%. So writing that as a decimal, it's 0.0175. There's 12 compounds per year, and it is n, the exponent, that I don't know. The next thing that I can do is we can do this division on the inside, 0.0175 divided by 12. Right? The order of operations specifies that I start inside the parentheses. So that gives a result of 0.001458. And I'll go ahead and do that in the denominator as well, so 0.001458. The next thing I can do is, again, inside the parentheses, I can add. So adding that gives 1.001458. At this point, I've kind of done all of the cleaning up I can, right? All of the simplifying I can. But what I can do now is I can start to solve for n. So we're trying to isolate this n on one side of the equation and move everything else over to the other side. So you kind of want to start on the outside and work your way in, or start with undoing any addition subtraction that you can do first. So that means this minus 325, I can add that to the other side. So adding 325 to both sides, that gives $23,757.12. After that, I can divide both sides by 325. So dividing both sides by 325, that will divide these 325s out to 1, right? So on the left-hand side, that will give 73.098831. On the right-hand side, the 325s are now gone. They've divided out to 1. The next thing I can do is multiply both sides by this denominator, by the 0.001458. Again, on the right-hand side, those will multiply out to 1. This was multiply. So on the left-hand side, multiplying those two numbers gives 0.106602, and we are almost there. Let me do better. That's 001458. So finally, I can add 1 to both sides. So that gives 1.106602 equals 1.001458 to the n plus 1. At this point, we want to bring that n out of the exponent. So the way to do that is by taking the natural log of both sides. Taking the natural log of both sides, we'll take that exponent and we'll turn it into a multiplier. What we mean by that is that we'll take the exponent and turn this into multiplication, like that. So then at this point we can divide both sides by the natural log of 1.001458. Right, that thing's just a number, so I can divide it over to the other side. So on the right-hand side, those natural logs will divide out. That will leave n plus 1. And on the left-hand side, this will leave 69.509704. One last step to solve for n, we can subtract 1 from both sides. So subtracting 1 leaves 68.509704, or rounding to the nearest payment is 69 payments. Again, I like to do just a quick check. My quick check is not perfect, but my quick check is to say, all right, if there's 69 payments and each month I'm investing $325, a future value somewhere near $22,425 would make sense. So my future value given was $23,432.12. So it makes sense that about $1,000 of interest would accumulate from this. Again, not a perfect check, but it's enough to say that yes, my answer of 69 is feasible.
Example 4. Many parents help their children save for college by investing a small amount every month into an annuity. Suppose a parent invests $80 every month into an ordinary annuity that has an interest rate of 2.8% for 18 years. For each part below, round to the nearest cent. How much money will the child have at the end of 18 years? How much of this money is money that was invested? How much of this money is interest?
I will start by writing down all of these variables and their values. So we do not know capital A. That is what we're asked to find. We know the regular payment is $80. We know the interest rate is 2.8%, or rounding that to the nearest, pardon me, not rounding, writing that as a decimal gives 0.028. I know that there are 12 compounds per year, which I know that a parent invests $80 every month, right? We're assuming that the investment is made every compounding period, right? So that would equal 12 compounds per year. And the total number of compounds is 12 per year times 18 years. So that would be 216 total compounds. Once I have all of the variables, I will choose the appropriate formula. This is the appropriate formula. After that, I will plug in my values. So it is capital A I want to find. The parent invests $80 every month. The interest rate as a decimal is 0.028. 12 compounds per year, 216 total compounds. Okay. So I will go ahead and start with the 0.028 divided by 12. So that gives a result of 0.002333. And same in the denominator, gives a result of 0.002333. Next, I will go ahead and add 1 inside those parentheses, so that gives 1.002333. Next, I can evaluate that exponent. So evaluating that exponent gives 1.654358. Then I can do the subtraction in the numerator. So that gives 0.654358. And then I can go ahead and do this multiplication and division all at once. So I can take 80 times 0.654358 divided by 0.002333.
And that gives 22,435.12548. Or rounding that to the nearest cent is $22,435.13. So that is the answer to part A. How much money does the child have at the end of 18 years? Part B asks, how much of this is money that was invested? So to find the amount of the money that was invested, we will take R, my regular investment, which is $80, and we will multiply by N, the number of investments. So the number of investments is 216. So R times N gives 17,280. That is the amount of money that was invested is $17,280. That's the answer for part B. Part C, how much of that money is interest? So to figure this out, we will realize, okay, the future value of the account is $22,435.13. The amount of money that was invested is $17,280. That means that the difference is the amount of interest that was earned. So the difference is $5,155.13. That means that this account earned $5,000 interest over the life of the account. This concludes example 4, and this concludes video 2.